We talk about optimizing right-of-way. So the issues are we want to either expand capacity in an existing right-of-way, acquire a new right-of-way, because we need new transmission lines to carry bulk power. We're getting power back from renewable sites. We've got solar ranches out in the desert. We've got wind farms up on mountain ridges located far from urban loads. We got to get that power back to where it's being consumed. We're also having new things. We're going to have, EPRI's been working on this for years with the IEEE. We're going to have EV charging stations. They're going to be on the interstates. They're going to be on 95, on 10, across the nation. So they're going to need some power. And then we've got new load centers for new load growth. I mean, people are moving to Florida, Texas, Arizona. They need a shot in the arm for bulk power. And lastly, climate change concerns. The American Society of Civil Engineers has rated the U.S. electric grid a D+. That's concerning for us electrical engineers. Naturally, the climate impacts only intensify threats to an already vulnerable infrastructure. If you've got a transmission tower that's 70 years old and it's getting near to an end of its useful service life and it gets hit by even a weak hurricane, you've probably got a problem on your hands. So these are some of the things we're thinking about. What are the challenges that we're facing here as an industry? We know the power gen has outpaced transmission line construction. We know that renewable power is expected to grow to 42%. 42% of generation by 2050, and approximately 1,000 gigawatts of clean energy production remain uncertain due to the lack of transmission infrastructure. We can't even put in these facilities because we don't have transmission facilities to bring it back to load centers. We know, secondly, the new transmission line permits are extremely difficult to attain due to environmental issues, social issues, political issues. It can take a decade, several decades before a permit is granted for a new transmission line construction. The continuous raising of energy consumption has put extreme pressure to utilities to find alternatives on how to increase transmission capacity. We know that the legacy transmission lines are old and outdated. Utilities are planning to increase the power output. In many cases, they have size restrictions for their existing right-of-ways. And lastly, we've got inclement weather as pushing transmission line design to be more robust. And when we say more robust, we're talking about weather hardening. We're talking about storm hardening. We're talking about wildfire mitigation. We have to think of all these things now when we're designing new lines and certainly new transmission lines. What is a transmission project lifestyle? Well, we got a feasibility study. We're going to do 12 months of routing and site survey, identify existing infrastructure. Where are the substations? Where can we build these? What are the routes going to be? We're going to identify environmental and permitting constraints, impact studies, then another 5 to 10 years right away in permitting, negotiating with landowners, easement acquisition, land clearing. That's a lot of work. Design, maybe 3 to 6 months, 9, 12 months of electrical study, line design, structure and foundation design. Get down to procurement. Hopefully that's going to take 6 months. We put 1 year here. Construction, we put 6 months. Might be 6 months, might be a little bit longer, depending upon how big the line is. Pour foundation, install towers, install conductors, etc. And then commissioning. So that project for new right-of-way can take 7 years if you're lucky, 7 years if you're darn lucky, more like 13 years. But if you got an existing right-of-way, it'll take you 1 to 2 years. So what's the difference between 1 to 2 years building a power line on an existing right-of-way and waiting 7 to 13 years to build it? Well, that difference should be more than intuitively obvious. So how are we going to optimize this right-of-way? Compact design allows utilities to optimize the existing right-of-way, resulting in a smaller footprint, decreased reliability. Covered conductors are going to mitigate wildfire risk. We're going to increase the capacity by overbuilds and underbuilds, substantial savings due to compact footprint. We're going to have carbon footprint reduction and a reduction of EMF fields. This is what it looks like. Right of way up is, how about if we took a look at, on the left, you've got a horizontal bare wire construction on an H-frame. So that's about 26 foot side to side with 115 kV spacer cable is 8 feet. So we're saving 18 feet on the width of that right of way. Not only are we saving 18 feet, but our 115 kV is taking about as much space as a typical 15 kV line. So we're talking different stuff here. How about vertical height reduction? If I look at the drawing on the left, is a vertical transmission, 115 kV bare, 27.5 feet. We go with spacing cable, it's 40. So now I'm saving 13.5 feet. Do you want to save 13.5 feet vertical height reduction? What is that savings? Are you saving on poles? What else are you saving on? How about a double circuit pole? Now you're saving 32 feet side to side width on that right of way. That's a heck of a lot of space. How about a double circuit? Double circuit on an H-frame. You don't want to put it on the same pole. You want to put it on two poles connected with an H-frame. Now you're saving 26 feet. Spacer cable, 115 kV versus bare wire. Massive, massive savings. Okay, so what are we allowed to say we're saving? We've got to do these calculations for the blowout because my right of way includes the blowout. There's the formulas. Basically, it tells us that we're saving so much on the width, and we're saving 2.25 acres per mile when we're building spacer cable versus bare wire for this case. The 2.25 acres per mile. Does that mean anything to you? Does that mean anything to your regulators, to your permitting, to the project, to your trimming? Anyway, we'll leave that to you. Power of quality, reduced voltage drop. We know we got 15 to 20% reduced impedance, 15 to 20% better voltage regulation, buying less aluminum, better end-of-line voltage. Fantastic. We know that because we're canceling out the EMF, we got 76% less EMF compared to bare and 82% less EMF compared to vertical construction.